The MH370 satellite video was not uploaded as a standard two-dimensional image sequence. The source file data structure is encoded in Stereoscopic 3D. It contains two separate video streams meant to simulate a binocular perspective. When we look at the raw source footage, we can see it is split into these two native channels. We are going to analyze the rendering mathematics required to fake the specific differences between these two channels. Generating true stereoscopic parallax requires a digital environment built in 3 full dimensions to calculate how objects shift relative to 2 offset lenses. If a creator fabricated this digitally, they would have to account for these shifts across every frame of the rendering data. The video format creates the technical baseline for our entire analysis. Military reconnaissance platforms use stereoscopic imaging because it allows for target mensuration. A single flat image cannot confirm a target height. Dual perspectives provide the data needed for precise altimetry and depth tracking from orbit. Dual offset sensors calculate distance by analyzing the visual shift, or parallax, between their two perspectives. This process relies on exact mathematical triangulation across the sensor payload to map the target position in space. Most public media and internet hoaxes rely on standard two-dimensional images. Hoaxers typically fabricate flat videos because they are easier to produce and distribute to a general audience. Doubling the rendering workload to create a multi-channel file increases the chance of technical errors and visual inconsistencies. Choosing a stereo 3D format aligns the data structure with established intelligence hardware standards rather than typical public leaks. We'll start by looking at a freeze frame of the airplane and the orbiting orbs in the split footage. We're measuring the parallax shift between the left and right perspectives. A difference mat subtracts identical pixels, highlighting geometric differences in white to show depth. Because the aircraft is closer than the ocean, its pixels shift laterally. Orbiting objects show specific pixel offsets based on position, while distant background clouds show almost no shift, appearing black. These mathematically consistent offsets indicate that the objects occupy specific points in a 3D coordinate system. To fake this in a 2014 compositor like After Effects, an artist would have to manually simulate these shifts. A simple 2D distortion filter can't replicate the complex pixel displacement required for true binocular disparity. This means the geometry of every object in the frame had to exist in a true 3-dimensional workspace. Let's look at the workspace required to build a scene like this. A standard fake only needs one virtual camera to render the final image. To place objects accurately in a 3D scene, artists use a Z-depth pass. This diagram shows a Z-depth pass. It assigns a grayscale value to every pixel based on its physical distance from the camera lens. Stereoscopic video requires 2 of these depth passes, calculated for 2 different camera positions, and they have perfectly synchronized. Artists often try to cheat this by stacking flat 2D layers in a digital environment. When you view flat layers through offset stereoscopic cameras, you get a cardboard cutout effect that exposes the lack of real volume. Avoiding this requires perfect precision in how every object's volume is calculated. Even a sub-pixel error in the Z-depth map would cause the stereoscopic image to jitter or flatten. The creator of this video had to maintain perfect geometric consistency across 2 simultaneous perspectives. Beyond the solid objects, we have to consider the most expensive elements in the footage. The video includes volumetric elements like complex clouds and atmospheric haze. We also see high-speed motion blur as the orbs move through that atmosphere. Calculating light scattering through volumetric fluids is a massive computational task that requires tracing light through millions of digital particles. Doing this for 2 separate cameras at the same time multiplies the processing power required for each frame. This chart compares render times for these types of volumetrics. The computational load for stereo rendering spikes exponentially on consumer hardware. Based on consumer hardware available in 2014, rendering these specific volumetric effects would have exceeded the capacity of a standard workstation. The presence of flawless stereo volumetrics suggests a level of hardware capacity that was not common for individual creators at that time. We can see how these constraints apply to the moment the plane disappears. This grid tracks the XYZ coordinates of the orbs circling the aircraft. The orbs move dynamically through the Z-axis, crossing in front and behind the plane's mass. The depth data remains consistent throughout the maneuver, showing no signs of clipping or depth mapping errors. A hoaxer doesn't gain any advantage by using a stereo 3D format. They only increase the complexity of the project. The parallax data in the footage matches the physical requirements of a real-world binocular sensor. Maintaining this level of consistency across every frame is difficult to achieve through simple trial and error. The footage behaves like a physical recording of a 3D event. We've looked at the technical pillars of this video's data structure: the parallax precision, the volumetric rendering requirements, and the synchronized depth passes provide a unified technical profile. When we analyze the video in 3 dimensions, the theory of a 2014 consumer-grade CGI hoax faces significant technical contradictions. Unlike known hoaxes that feature clipping and depth errors, this footage maintains mathematical alignment across both channels. This level of consistency aligns with the output standards found in intelligence hardware. The stereoscopic data is a native feature of the sensor platforms used for this kind of reconnaissance. The evidence shows that the file structure is consistent with professional multi-channel hardware output. The stereoscopic format provides the technical data needed to verify the spatial reality of the MH370 satellite video.